So this exercise is related to acid-base equilibrium. First is question number 9. The MCQs related to the topic. In question 9, when a small amount of a hydrochloric acid is added to a buffer solution, the change in the pH is very small. So there is a change in pH, but relatively very small change in pH. What could be the reason for that? Why the pH does not change too much? So the main, when we work out, as we know, like the pH, if we write the dissociation equation for the any acid, like example, because what are buffer solution? Buffer solution is a mixture of a weak acid and its salt or weak base and its salt. So if we write dissociation constant for acid or a base, like say we were having a buffer solution of ethanoic acid, so this will dissociate into CH3COO H plus, and if we have its salt CH3CO Na is there, it will dissociate into CH3CO plus Na. So what we have excess or a bulk of the negative ion. And if when we write the equation for the first equation, when we write the value for Ka, so when we write the value for K is the product divided by reactant. So what is the product? The product is CH3CO. Hydrogen ions are there. And what is the reactant? The reactant is acid, CH3COH. So how we justify that the pH of a solution is not changing? So because the pH of a solution depends on the hydrogen ion concentration. And the hydrogen ion concentration depends on the concentration of, if we like move to other side, so this will be Ka, the concentration of the CH3COH acid, and concentration of the salt, which is a conjugate base, CH3CO negative, and this is H plus. So if we want to find a hydrogen ion, this is moved to numerator and this one is moved to denominator. So hydrogen ion is dissociation constant of acid, or if it was a base, dissociation constant of the base time the concentration of acid divided by the concentration of conjugate base. So because this ratio, K is a constant thing for at a fixed temperature, because K depends on the temperature. So at a constant temperature, K does not change. So how the pH of a solution is not changing, or a very small change in pH, because this ratio between the acid and its conjugate base does not change. When we add an acid or we add an alkali, because this ratio is not changing, that's why the hydrogen ion concentration does not change. If hydrogen ion concentration does not change, the pH of the solution will not change. So when we check what is the best explanation for this, so because here the dissociation of acid in a buffer solution is small. The buffer solution acid is dissociating. So this statement does not give an idea. The concentration of a buffer solution only changes little. It's not about the concentration of a buffer solution. It's about the ratio between the conjugate acid and its salt, or we can also say acid and its conjugate base. So the ratio of the concentration of acid to conjugate base in a buffer solution does not change. It's written does not, there is a change, but there is a slight, very small changes there, or a little changes there. So ratio of the concentration of acid to conjugate base in a buffer solution, there is a small change. That's why the pH will change, or a hydrogen ion concentration will change, but it will be a very small change. Is it clear? Question 9. So when we add a small amount of acid or an alkali, this ratio there will be a very small change in the ratio, as we have a plenty or a bulk of, because we have the bulk of these ions, this ion is coming from, the conjugate base is coming from acid as well and the salt. So we have a bulk or excess or a plenty of these ions. So these ions are so much that if even a small change in number is there, that overall change will be negligible. So this was question 9, then question 15. In question 15, what is the approximate pH of a buffer solution which contain 0.2 mole of a weak acid, and pKa is given 4.8, and 0.2 moles of a sodium salt of the acid, which is having a volume of 1 uh, dm cube of a solution. The total volume is 1 dm cube. So how we can work out the same thing, like if we have acid is there, weak acid is there, Ha. So this weak acid will dissociate into H plus and A minus. And we have, so if I write the dissociation constant for this, it will be a product divided by reactant. So hydrogen ion is there, A minus is there, divided by concentration of hydrogen, not iodide, it's A, like it can be any anion. That's why it is written generally A. Now, the salt of that anion, it will dissociate into Na plus and A minus. Now, using this equation, we have to work out the hydrogen ion concentration, and from hydrogen ion concentration, we can work out the pH. Or you can rearrange this equation and you can convert into pKa as well. So, or from this pK, we can find Ka. How we can find, because the formula is pKa is equals to minus log of Ka. So if the pKa is equals to minus log of Ka, it's same like pH is equals to minus log of hydrogen ion concentration. So pKa is equals to minus log of Ka. If we take anti-log both sides, so 10 raised to power minus pKa is equals to Ka. Same way, like if I need a hydrogen ion concentration, so 10 raised to power minus pH will be equals to the hydrogen ion concentration. So same way, 10 raised to power minus pK will give us the value for K. So we substitute the values. The value of the K will be 10 raised to power minus pK. So 10 raised to power minus pK means 10 raised to power minus 4.8. We substitute that. Then hydrogen ion concentration, we don't know. What about the concentration of the N ion? If we have 0.2 moles of a sodium salt, like if this was 0.2 moles, it will dissociate into 0.2 moles of sodium and 0.2 moles of negative ion. And the volume of a solution is 1. So if we want a concentration, these are the moles. If we need a concentration, we divide by volume. Because the volume is 1, so in this case, the moles and the concentration will be same. So we write 0.2 here. And what about the concentration of the acid? As I mentioned here, the 0.2 moles of a weak acid. So we have 0.2 moles of a weak acid, and we assume that it does not dissociate. So its mole does not change. And what about the concentration? Because the volume of a solution is 1, so the moles and the concentration will be equal. So when we simplify, 0.2 will cancel with 0.2. So what we'll get? We'll get 10 raised to power minus 4.8. So 10 raised to power minus 4.8 is equals to hydrogen ion concentration. And After getting a hydrogen ion concentration, you'll use the formula pH is equals to minus log of hydrogen ion concentration. So you use the formula pH equals minus log of hydrogen ion concentration. So you substitute this value here, you will get the pH of a solution, which will be 4.8 as well. So C will be the right answer. There's also another way to do this question. Direct method is there. As you can see, like when we talk about the hydrogen ion, like Ka is equals to concentration of the negative ion, concentration of the hydrogen ion, and the concentration of the acid. In the question, we have equal concentration of acid and its salt. So if they have the equal concentration, they will cancel out. So in that case, Ka is equals to hydrogen ion. And when Ka is equals to hydrogen ion, it means Pk is equals to pH. So Pk will be equals to pH. So Pk is 4.8. So pH should also be 4.8. That's why C will be the right answer. So both ways you can use to solve. Is it clear? This question 15? Next is question number 19. A solution of a weak acid cannot be titrated with a weak base using an indicator to find the endpoint, because usually what happens when we have a weak acid and weak alkali, we cannot because when we sketch a graph for the pH and the volume of acid or alkali added, so what will be the shape of the graph? So this will be the shape of the graph. We don't have a vertical part, or pH is very like the pH change is too gradually close to the equivalent point is there. So it's not about the indicator. There are too few hydrogen ions affect the indicator. The first one, the pH change is too gradually close to the equivalence point. Like if we have an equivalence point and the change in the pH near the equivalence point, that is too close. That's why it is difficult to select a proper indicator. Because usually when we select an indicator, we select, go for the vertical part. Like we check this range, the indicator, like the pH is changing, say from 2 to 11. So we can select an indicator, any indicator within this range, which show a color change from 2 to 11. But when we use a weak acid and weak alkali, the change in the pH is too gradually close to the equivalent point. That's why it is difficult to use any specific indicator, or we don't have a vertical part. So A is the right answer. There are too few hydrogen ions that, in fact, that's not correct. Hydroxide also not correct. pH change occur outside the range. So we cannot not even have an indicator which shows a very small range, because indicators also have a range, specific range is there. So we don't find any indicator for a vertical portion, as there is no vertical portion for the weak acid and weak alkali types. Next is question 22. Question 22, what is the pH of a following solution? 22 part D is there. A buffer solution is prepared by mixing 20 cm cube of 0.1 mole per dm cube methanoic acid with 10 cm cube of 0.1 mole per dm cube sodium hydroxide. Given that the pKa of a methanoic acid is 3.8, what is the pH of a solution? So how we can work out the pH of a solution for buffer solutions? So Ka, dissociation constant, is equals to the concentration of, because here what we have methanoic acid. So methanoic acid is HCOH, will dissociate into H plus and HCO negative ion. And its salt is there, sodium methanoate, which will dissociate into methanoate ion plus sodium ion. So when we write the equation for the first part, we write dissociation constant Ka for the methanoic acid is a product divided by reactant, so concentration of hydrogen ion, concentration of methanoate ion divided by concentration of methanoic acid. Now, when we mix the two solutions, like here 20 cm cube is there and here 10 cm cube. So when we mix them together, the new volume of a solution will not be 10, 20 or 10, it will be 30 cm cube. So the concentration of both ions will change. We have Ka, as I mentioned, we have pKa. How we can find the Ka? As we have the formula, K is equals to 10 raised to power minus pK. So that will give us the value for K. So we'll have 10 raised to power minus 3.8. This is value of K. Hydrogen ion concentration we have to work out. Using a formula. Then what we have HCO negative is there and HCOH is there, the acid. So we have to use a formula to work out the concentration of the negative ion and the concentration of acid. So how we can use that? If we write the equation, because the sodium hydroxide is reacting. So what is the buffer solution? A solution which is having like a weak acid and its salt or weak base and its salt. So when we have methanoic acid reacted with sodium hydroxide, it will form sodium methanoate plus water. So the ratio between them is 1:1. Now, when we work out like how many, because the thing is, if we want to work out the hydrogen ion concentration, first we have to know how many moles of salt will be there and how many moles of acid will be there. So when we mix 20 cm cube of 0.1, so 20 cm cube means like 0.02 because we divide by 1000 and this is 0.1. So when we multiply, it will be 0.002 moles will be there for methanoic acid. So we have 0.002 moles of methanoic acid. How many moles of sodium hydroxide are there? This will be divided by 1000, so 0.01 and this 0. So when we multiply, we'll have 0.001. So ratio is 1:1. If ratio is 1:1, how many moles, like this will be a limiting factor or a limiting reagent. Sodium hydroxide will completely used up. So we're left with 0 moles of sodium hydroxide. And because ratio is 1:1, if 0.001 moles of sodium hydroxide, how many moles will be left for methanoic acid after the reaction completes? 0.001. Because like 1:1 is the ratio, 0.01001 will react with the same amount. So if total was 0.002, so when we end the experiment, we'll have 0.001 moles of methanoic acid. And how many moles of salt will be there? Because we work out the moles of a product by using a limiting factor. So ratio is 1:1. So how many moles of salt will be there? 0.001. So now we have the moles of the methanoic acid, new moles of methanoic acid, and the new moles of the salt. And how to work out their concentration? These are the moles. We have to work out the concentration, moles divided by volume. So 0.001 divided by volume. Now, because the two solutions are mixed together, 20 cm cube is mixed with, like, this was 20 cm cube and this was 10 cm cube. So when they are mixed with each other, it makes 30 cm cube. So the new volume is 30 or 0.03. So 0.001. So 0.001 divided by 0.03, which will give us 0.033 moles. And this will also be 0.033 moles. Now, moles per dm cube, the concentration, because this is 0.001 divided by 0.3 will get the same amount. As I meant, if we have the equal moles of a salt and the acid, what will happen in that case? Because we have the formula K is equals to concentration of salt times the concentration of hydrogen ion divided by concentration of acid. If we have salt and acid in the same concentration, so it will simply cancel out each other. If you have equal number of a salt and the acid, they simply cancel out each other. So when they cancel out each other, we can say Ka is equals to hydrogen ion concentration, or we can also say Pk is equals to pH. So Pk and pH will have the same value. Because the Pk is 3.8, so pH will also be 3.8. So B will be the right answer. Is it clear, this question? So for buffer solutions, when the concentration of a salt and the concentration of acid is equal, in these questions, the pH of a solution will be equals to pKa, or Ka will be equals to hydrogen ion concentration. Any doubt in this one? So first we work out like how many moles of acid will be left after the reaction. Then we work out how many moles of a salt will be there formed when the reaction ends. Because it is forming equal number of the moles, or it will have the same concentration, the final solution. So the concentration of salt will cancel with concentration of an acid. So the pKa in Ka will be equals to hydrogen ion concentration, or pKa will be equals to pH. Next is question 27. So you can also like pH is equals to pK plus log of a salt divided by acid concentration. You can remember this formula as well, or you can, so even we can use this formula, but the high concentrations are same. So this factor will be 0. And when this factor is 0, the pH and pK will be equal. This is what we did in the previous question. Then 27 and 33. The dissociation constant of a water Kw increases with the increasing temperature. What happened to the water? Like when dissociation constant increase, look, the dissociation constant for water. So water will dissociate into H plus and OH minus. The forward reaction is endothermic. So if we increase the temperature, equilibrium shift toward right hand side. If equilibrium, like say we were having 10 molecules of the water, out of 10, 2 molecules dissociate when the temperature was 25. But if we increase the temperature to 35, as a result, what will happen? Out of 100 molecules, maybe 15 molecules will dissociate. If you further increase the temperature to 45, out of 100 molecule, maybe 25 molecule will dissociate. But water, why the water will remain neutral, even though the pH of the water will decrease, because hydrogen ion concentration increases, more hydrogen ion, pH will be less, but water will not become acidic. Why it won't become acidic? Because when two water molecules dissociate, it produces two hydrogen ions and it produces two hydroxide ions. The substance become acidic or alkaline if the number of the hydrogen ion and the hydroxide ions are different. But what happened when we increase the temperature? There are more hydrogen ions, like at 35, there will be 15 hydrogen ions will be there and 15 hydroxide ion. Because the hydrogen and hydroxide number is same, that's why the water will be neutral. Same thing, if we increase the temperature further, 25 hydrogen ions will be there and 25 hydroxide ion. But again, the water will be neutral because it has equal amount of hydrogen and hydroxide ion. But when we talk about the pH of the water, Like at 25 example, if it was 7, at 35, it might be 6.9. At 45, it might be 6.7. So when the temperature of a water is increasing, why the pH is decreasing? Because pH depends on the hydrogen ion concentration. pH is equals to minus log of hydrogen ion concentration. As the hydrogen ion concentration increase, the pH will decrease. But even this decrease in pH does not mean that the water will be acidic. Why the water is not acidic? Because if it produces 2 hydrogen ion, it will have 2 hydroxide ion. If it produces 15 hydrogen ion, it will produce 15 hydroxide ion. Because the number of the hydrogen ion and the hydroxide ion is changing by the same factor, that's why it remains neutral. And the pH will decrease. If the question was about what happened to the pH of water, that will decrease because the pH depends on the hydrogen ion concentrations. Is it clear? Question 27. Next is question 33. A solution of a hydrochloric acid has a pH of 3, and when it is made 10 times more dilute, the pH is. So what is the effect? Because pH is equals to minus log of hydrogen ion concentration. If we, the relation between the hydrogen ion and the pH, that is inverse. Like if the solution hydrogen ion concentration increase, the pH of a solution will decrease. And if we have less hydrogen ion, then the pH of a solution will increase. If not hydrogen ion concentration. So what we did, we made the solution 10 times more dilute. So if we make the solution dilute, what happened to the hydrogen ion concentration? Hydrogen ion concentration will decrease. So if the hydrogen ion concentration is decreasing, means the pH of a solution should increase. So it cannot be A, it cannot be B. And because it's an acid, so it cannot be D as well, because the solution can be, it's an acid. Acid cannot have a pH 13. So it will be C. And you can also understand from a factor, when a log is changed by factor 10, like example, say we were having pH is equals to minus log of hydrogen ion concentration. If the pH was 3, when the hydrogen ion concentration is a certain number like 0.001 was there. If we multiply, like if we make it 10 times more dilute, means we reduce the concentration. So if it is divided by fact, because if a volume is increased, like dilution means like volume increase. If a volume is increased by 10, the concentration will decrease by 10. So if this is changed by factor 10, because it's a log here. So when it is a log, when a log is changed by factor 10, then the number will change by factor 1. Like if I take a log, if I take a log of 0.1 and I take a log of 0.001, so how many times we change the number? Like, or if I take 0.01, so how many times we change the number? We change the number by 10. So if we like divided by 10. So if we divide by 10, factor 10, what will happen to the value of a pH? It will change by number 1, like factor 1. So this was like pH 1, so this will be pH 2. If we change the concentration to 0.001, means from the original value, we have decreased by 100. So if we divide it by 100, what will happen? It will increase by factor 2, because like 2 zeros are there, so it will increase by factor 2. So this will be pH 3. So relation between the log and the pH, if it is multiplied by 10, it will increase by number 1. If it is divided by 10, it will decrease by number 1. So as a result, what happened here, as a solution become more dilute, means the volume is increased by factor 10 or the concentration is decreased by factor 10. If the concentration is decreased by factor 10, what happened to the pH? The pH will increase by factor like 1. So, and if it was divided by 100, this will increase by factor 2. If it was divided by 1000, it will increase by factor 3. If it is divided by 10,000, it will increase by, so how many zeros are there? The same number, it will increase or decrease. If it is divided, other will increase. If it is multiply, other will decrease. So C should be the right answer for this question. Any other question or doubt from this exercise? Acid-base equilibrium.